This is the Automated System for Wet Lab Operations in Microgravity, MMEC, Senior Capstone Project. Our group consists of 7 team members who are Carpenter, David Kirchev, Callan Leonard, Josh Mack, myself, Muhamed Polovina, Poff, and Aaron Thomas. The objective of our project is to design and deliver an automated drop tower testbed for wet lab component research and development and validation. Our sponsor, IRPI LLC, wishes to streamline product validation of capillary fluidic system hardware specific to wet lab operations in low-gravity environments using such a device. Essentially, our goal is to create a microgravity test apparatus, which we call the MGTA, that would meet the predetermined objectives that we were given while taking into consideration reliability, repeatability, and user-friendliness. Our sponsor, IRPI, provides research, engineering, and development services for the aerospace, medical, energy, and defense industries, and have worked with companies such as NASA, SNC, Honeywell, JPL, and Tupperware brands. They specialize in designing, developing, and operating space hardware for things such as life support, waste management, space habitats, thermal management, and so forth. IRPI is also recognized as a world leader in microgravity research and has been developing systems, devices, and experiments for drop tower tests, aircrafts, and in-space platforms such as the International Space Station. PSU has granted us supervised access to their Dryden drop tower located in the engineering building for testing purposes. In general, drop towers can simulate microgravity conditions reaching as low as 10 to the negative 6 G. The Dryden drop tower at PSU can simulate as low as 10 to the negative 4 G, while free-falling a total distance of 22 meters, or 72 feet. The total drop tower height is 31.1 meters, or 102 feet. The anticipated low G duration during drops is around 2.1 seconds, which equates to the amount of time we have to execute our programs. The object falling in the drop tower experiences an average deceleration force of 8.5 Gs and a peak deceleration force of 15 Gs. Here's the drop tower in action with Jesse Goodman as the operator. There are microphones and speakers installed to help communicate to floors below that a drop is about to occur.
2, 1, drop!
Our sponsor, IRPI, has indicated that the system we design must be able to detect low G and initiate a pre-programmed sequence of operations for fluid transfer, including fluid insertion, extraction, mixing, and other future operations. The system must be able to commute with various probes, tips, and cannula, and must complete test operations within the 2.1 second test window. The system must be able to terminate operations upon deceleration and withstand repeated use under PSU's drop tower deceleration conditions. IRPI also provided us this figure showing an example of an illuminated visual field of view of operations. The majority of the parts in all of our prototypes were custom designed and manufactured in-house by our team using SolidWorks, Michael's CNC mill, 3D printer, and bandsaw. Here's a shot of the 3D printer making the initial electronics case for the first prototype. For the most part, we used either red or gray PLA Pro, PLA Plus 3D printer filament for the printer material. The first prototype was our proof of concept, as it was an attempt to see if our collective ideas regarding the MGTA would work. We designed a standalone system which would be placed into the aluminum shell provided by IRPI and PSU. The foundation of the system was made from T-slotted 6063 T5 aluminum extrusion held together by metal brackets and screws. We attached a linear Z-axis ball screw with a built-in stepper motor which gave us 100 millimeters of travel up and down. This was our first electronics control test with the ball screw. We had a sliding bed, which was attached to 2 linear guideways coupled to a single stepper motor. The bed could move back and forth in a single direction at variable speeds, and was designed to allow different well plates and objects to be attached to it. We bolted the frame of the system onto the aluminum shell, restricting movement of the MGTA while free-falling in the drop tower. The custom-made electronics case housed the 32-bit panel board controller, a Raspberry Pi for later use, and an accelerometer which we use as a triggering mechanism for the programs once sensing low G. After compiling the board firmware and troubleshooting the software, a few dry runs, and ensuring that the rig was balanced, we were ready for our first test drop, which ended up validating our system functionality. This video shows the program we wrote successfully initiated once the trigger sensed low G. After some feedback from our PSU advisor, Mark Weisslogel, and our sponsor, IRPI, we introduced our plans for a second prototype, which would be attached directly onto the aluminum shell we were provided. This eliminated the sliding bed and in turn allowed the probe head to move in all three directions at variable speeds. We were able to reuse most of the frame components from the first prototype with some minor adjustments. We also created a new lighting system made from LED strips with a diffuser attached on top. This updated design allowed us to use the existing mechanism attached to the drop tower to move the MGTA into and out of the drag shield with more ease. This was one of the repeatability tests we ran on the second prototype, which also verified smooth motion in all three directions. We were able to attach our custom-made fluid pump powered by a stepper motor connected to the main board. Here's the system in action with the pump inserting and extracting liquid through the needle attached to the probe head. We were able to run a few drop tests with the second prototype and gather vital data which allowed for further analysis. Using data collected from an IMU attached to the MGTA during several drops, we confirmed that the maximum impact forces reached about 15 Gs during deceleration. This data was then used to simulate drop conditions using finite element analysis software, which allowed us to continue studying the forces and deformation on the different subsystems in our models. The data we captured for our second prototype showed an overall factor of safety of about 80, which means that this model was over-designed. The issue we discovered was, because the probe head, which was fairly heavy, hung off of the two support rods, it acted like a cantilevered beam. Because the center of mass was offset from the center of geometry, when acceleration was applied downwards, the probe head wanted to twist the two rods, creating a moment. We actually saw the two support rods twist out of position slightly with each drop, even though they were both secured to the frame. For this reason, we adjusted the design again in the third prototype, eliminating a lot of unnecessary weight, and reduced the factor of safety to a more reasonable value of 3.7. We moved the stepper motor down and behind the linear rail, which acts as a support rod. The center of mass is now roughly on the bearings, which should result in much less twist. Maximum vertical displacement stayed below 0.25 mm for both the second and the third prototypes. This is our third and final prototype and is the culmination of our research and experience gained throughout this last year. Many components of the second prototype were changed with this new design, which allows for more space inside of the rig, better access to all of the components, and a more sophisticated probe head, or end effector. As you can see, the final prototype now has two different pumps connected to different probes, with a new mechanism allowing for interchangeable tips on each one. We have two smaller cameras for user visibility, a larger LCD screen attached to the front, which has an SD card slot on the side, and an integrated electronics case housing all of the important components which make the MGTA work. In order to preserve the two 12-volt batteries that we have, we connected the system to a designated power supply shown on the right. The electronics case has our sponsor's logo imprinted on it and an opening for the heat sinks on the stepper drivers. There are also openings along the sides allowing for airflow coming in from the fan, which we have installed on the left, which should prevent overheating of the system. The LCD screen is depicted here by the black arrow on the bottom. Its case houses an Arduino on the back side with an integrated accelerometer which we use as our trigger. The electronics case itself contains four separate components. The main 32-bit SKR controller is shown by the red arrow, and the stepper drivers, which sit on top of the SKR controller, and their heat sinks are shown by the orange arrow. We also have a voltage step-down regulator, shown by the blue arrow, which provides a step down from 12.8 volts to 5.2 volts, which powers the Raspberry Pi. Unfortunately, the main controller does not have an onboard voltage regulator like some other microcontrollers, which is why we needed to install the voltage step-down regulator. The last component is the Raspberry Pi, shown by the green arrow, which is formatted with an open-source 3D printer software called Octoprint. This software allows us to connect to the system via an Ethernet cable attached to the Raspberry Pi or via Wi-Fi. Octoprint also allows for live access to the system with on-screen controls and access to the webcams placed inside of the rig. The user can retrieve the exact coordinates of the wells they are trying to integrate into their program using this software. It can be run on any computer regardless of which operating system is installed. Here are a few pictures of the electronics case with all components connected and its cover. This is the 32-bit main controller, with everything plugged in and cable managed. This is the voltage step-down regulator, and this is our Raspberry Pi at the bottom. We also have a small fan installed on the left which has a custom vent attached to it. This fan helps cool the system after long periods of use. There are a total of 6 stepper motors installed, 2 of which are mechanically coupled, which allow the MGTA probe heads and pumps to be moved by the user, either through a pre-programmed code or by using the LCD screen and knob in the front. We also have a battery case which holds the 2 12-volt batteries down to the bottom of the aluminum shell. The test bed and well plate attach pieces were also custom designed. The bed features screw nuts installed in each hole, allowing the feet to be fastened into place, which secure the well plate from any motion during drops. What's neat about this final design is that the user can complete multiple tests with different fluid types using the 2 separate pumps. They can even do tests with fluid mixing without contaminating both fluid sources. Both pumps can insert or extract liquid at variable speeds. One of the pumps is larger, giving it the ability to exert more pressure since its control volume is also larger. Here's a video of the smaller pump in action using the knob attached to the LCD after running through a calibration algorithm. We had a few electrical problems with the first iteration of our lighting system, so we decided to attach new LED strips along the ceiling of the aluminum shell. The new LEDs are capable of outputting 450 lumens, and we left an additional cable disconnected in case our sponsor needed to attach an additional strip for more light. Our team, the capillary crew, was able to successfully meet all of the aforementioned objectives set by our sponsor and PSU advisor. We were able to successfully preload programs written in G-code, which are initiated when low gravity is detected by the accelerometer trigger. The firmware in the controller has the ability to terminate the program once deceleration is complete, but we have left this feature off as we were unable to test or calibrate the feature due to current COVID-19 conditions. We confirmed that the MGTA maintained its structural integrity by physical tests for the first and second prototypes. Given that the campus closed due to COVID-19, we were unable to perform physical testing of our final prototype, but ran multiple FEA simulations instead, which showed an overall factor of safety of 3.7. We have ample lighting with our LED positioning and ample space for the phantom camera, which is set to arrive soon. The MGTA is highly modular and can insert and extract fluids with adjustable flow rates. The translational speeds of the MGTA in the X, Y, and Z directions are capable of reaching above the 1.5 meter per second requirement. The user is also able to attach a variety of different probes and tips to the end effector, given the nature of its design. Repeatability tests pass for the accuracy and precision of the end effector or probe heads with respect to the well plate that the fluid is inserted into or extracted from. The MGTA also has a user-friendly interface with the ability to modify G-code programs remotely or via an SD card which is included. The internal components are all easily accessible if adjustments are deemed necessary. With the final design, we also reduced the magnitude of the angular displacement of the MGTA, preventing spilling of samples in the wells of the well plate. The following is an example test sequence. The text file containing the G-code for the program is uploaded onto an SD card which is inserted into the side of the LCD housing, or onto the Raspberry Pi from the Octoprint server depending on what the setup is. When the MGTA is loaded into the drop tower, the controller waits for the trigger to initiate the sequence. The trigger was designed to be initiated either by the accelerometer when detecting low gravity, or via a push of the front knob. This is an example test recorded in slow motion showing both pumps and probe heads in action. Here's the same test in real time. Here's another test that we ran for a PSU grad student with our second prototype. They were trying to see how far the viscous fluid bridged when the syringe was removed from the well. The angle of the camera did not capture the entire length of the fluid bridge, so we added a mirror to the back of the test bed and adjusted the angle of the camera to get a better view of the phenomena occurring. As we did not have access to the drop tower for the majority of the spring term, we were unable to test our last prototype. Because of this, we were not able to calibrate the sequence termination function once the MGTA completes deceleration. A series of drop tests should be run to confirm the functionality of the accelerometer trigger, as well as to confirm the structural integrity of the MGTA and the results of our FEA simulations. As we did not receive the Phantom camera, we were unable to create a platform to mount it onto. We did leave ample space for a camera mount to be installed, which will need to be completed at some point in the future. Our team believes that this was a successful Capstone project. We hope that our microgravity test apparatus, which we named the MGTA, will be used for further studies and help alleviate the complexities of setting up an experiment from scratch to test fluid phenomena in low-G environments. I want to thank our team for sticking together and finishing this project despite our circumstances due to COVID-19. A special thank you to Michael Poff for volunteering to take on the majority of the physical build for the last prototype at his home, as we were unable to continue working on the rig on campus. We started with an idea, refined it, and created a working final product in the end.